Have you ever been chatting with an AI and just stopped and wondered, how is it doing that? How does it seem to get what you're saying, to reason, and to write things that feel so human? Well, today we're going to pull back the curtain on the magic behind these digital minds. We are diving deep into the world of large language models.
Okay, so to really get how these things work, let's start with a really simple idea. Picture this. You find a movie script. You can see the user's line, but the AI assistant's response is totally ripped out. And your one job is to figure out the very next word the AI would say, then the next one and the one after that, until you've built a whole response. That simple act of just predicting the next word, that is the absolute core of how these incredibly powerful AIs operate.
And that right there brings us to the main event, the definition of a large language model, or an LLM. At its heart, it's really just a super sophisticated mathematical function. Its one and only job is to look at some text and predict what word comes next. But here's the really clever part. It doesn't just pick one word. It looks at every single word it knows and assigns a probability to all of them, creating this ranked list of the most likely candidates to show up next.
So we've got this incredible prediction machine. But how does that actually translate into the smooth, natural conversations we have with chatbots every day? Let's break down how it really happens, step by step.
It all works in this constant loop, which you can see laid out right here. It all starts with step 1. Before you even type a single letter, there's this hidden prompt that sets the stage, telling the AI its role, something like, "You are a helpful AI assistant." Then, step 2. Your question gets tacked onto that. Now the magic happens in step 3. The LLM predicts the first word of the answer, then feeds that back in to predict the second word and the third, over and over and over again. Finally, once it predicts a natural stopping point, the whole response is shown to you in step 4. And this entire cycle happens in literally the blink of an eye.
So this brings up a really good question. If it's all just a big math problem, shouldn't you get the exact same answer every single time you ask the same question?
And the answer is, surprisingly, no. And that's exactly what makes it feel so dynamic. To keep from sounding robotic and to seem more natural, the model is actually designed to throw in a little bit of randomness. Instead of always picking the number 1 most probable word, it might randomly choose from, say, the top 5 or 10 most likely words. So here's the takeaway. The model itself, the math behind it all, is totally consistent. But by adding just a small controlled dash of randomness to its word choice, the final answer you see feels fresh and different each time.
Okay, so we know it's a prediction machine, but how on earth do you actually build one of these things? The answer comes down to 2 things, a mind-boggling amount of data and the level of computation that's almost impossible to imagine.
It really boils down to 3 core ingredients. First, you need a truly staggering amount of text. We're talking a huge portion of the entire internet. Second, you need a model that has billions of tiny little knobs, or dials, that can be tuned. These are what we call parameters. And third, you need a training process to painstakingly adjust those billions of dials over and over and over again.
Now, just to put that enormous amount of text into perspective, for a model like GPT-3, if you were to sit down and just read all of its training data 24/7 without stopping, it would take you more than 2,600 years. And that was an older model. The new ones are trained on even more. It's just wild.
And if you think that number is crazy, just wait till you hear about the computation. Let's say you could perform 1 billion calculations every single second. Even at that speed, it would still take you over 100 million years to do all the math required to train one of these giant models. It's a scale that is truly difficult to wrap your head around.
So how does this training actually work? Well, the model starts with all those billions of parameters set to totally random values, which means its first outputs are just complete and utter gibberish. But then it gets shown an example from its training data, it makes a prediction for the next word, and it compares its guess to the real word. An algorithm then jumps in and slightly adjusts all those billions of dials, just nudging the model to be a little bit better next time. Now, repeat that process trillions of times, and slowly that gibberish starts to transform into coherent, meaningful language.
But there was a huge problem. Doing this many calculations was just flat out impossible with the older AI designs. To handle this incredible new scale, we needed a completely new kind of digital brain. And that breakthrough is called the transformer. The difference here is just night and day. Old models had to read text 1 word at a time in a straight line, kind of like we do. It was incredibly slow and inefficient. Transformers, on the other hand, can basically just soak in the entire piece of text all at once, processing everything in parallel. This ability to work in parallel is the key. It is the innovation that unlocked the power to do those 100 million-year calculations in a matter of months instead of millennia. And the secret sauce inside every transformer is a mechanism called attention. Just like the slide says, it allows all the words in a sentence to talk to one another. Basically, for every single word, the attention mechanism is weighing how important every other word is for understanding its true meaning. So if the model sees the word bank, attention lets it look at the surrounding words, like river or money, to figure out the right context. Are we talking about a river bank, or are we talking about a financial bank? That's what attention does.
But all of this incredible tech, all this raw power, it just creates a really, really good autocomplete machine. It doesn't create a helpful AI assistant. For that, you need one last absolutely crucial ingredient: people.
You see, this whole process really happens in two very different stages. Over on the left, you've got pre-training. The goal here is simple: become an expert at finishing sentences from the internet. The method? Just predict the next word, trillions of times. The outcome is a raw model that knows a ton, but it's not an assistant yet. That's where phase 2 comes in, human feedback. Now the goal completely changes. It's about becoming a helpful and harmless AI. Here, humans actually rate the AI's responses, giving a thumbs up for good answers and a thumbs down for bad ones. This feedback is what fine-tunes all that raw knowledge, shaping it into the useful, friendly chatbot we all interact with.
So we've covered the data, the architecture, and the human feedback loop. But that brings us to the most baffling, most mysterious part of this entire story. Even the people who create these things don't fully understand how it all works.
The key phrase to focus on here is emergent phenomenon. Think about it. Nobody programmed a poetry writing module into these AIs. Nobody coded a write computer code function. Those incredible abilities simply emerged as a side effect of training the model to do one simple thing: predict the next word, at a massive, massive scale. The researchers built the learning framework, but the specific, complex behaviors that arise from it make it almost impossible to trace back and say exactly why the model gave one answer instead of another.
And that leaves us with a pretty profound final thought. We've built these incredibly powerful tools that are already starting to reshape our world. But if the specific logic behind their reasoning is an emergent mystery, even to their own creators, what does that mean for our future with them? That's a question we're all going to have to think about as these tools get woven deeper and deeper into our lives.